Hi everyone, welcome to this talk. As you could see on the title slide, I will be presenting the result of a joint effort today of a large and diverse group of people who are collaborating in a Belgian consortium that I'm coordinating, the InSight project. I will say more about that in a minute. And we are very happy that we can speak in your DH lecture series in Kraków, even if it is only virtually. As you might know, there is a very special connection between Flanders and Poland in the world of digital humanities, and I'm delighted that we can honor that connection with this talk. So let's get started. So first, a bit of context, which is the InSight project. This is an acronym for Intelligent Neural Systems as Integrated Heritage Tools. In this project, we collaborate with 3 Belgian universities, Liège, Ghent, and Antwerp, where I am, and 2 museum clusters in Brussels. These are federal heritage institutions, which is a bit uncommon in Belgium, since most museums are actually funded at a regional level in our country. And that also explains why this project is funded by BELSPO, which is the federal funding agency for science in Belgium. The aim of this project is to advance the application of artificial intelligence, machine learning more specifically, in the museum world in Brussels. And specifically our 2 partners, the Royal Museum of Fine Arts and the Royal Museum for Art and History. More specifically, we aim to leverage AI technology to support smaller heritage institutions in their digitization and cataloging efforts. Often these smaller museums have only a limited budget or staff for this kind of work, and we are exploring how AI can help them and support them in digitizing, exploiting, but also opening up their collections. This is a very broad topic, of course, and today I will be focusing on a more specific part of our project, which lies in something called music iconography. This is a scholarly field, maybe one that you have never heard of before, but a very interesting one, as we hope to demonstrate today. Broadly speaking, music iconography is the part of the humanities that studies how everything related to music is depicted in the visual arts. This could be representations of musical instruments, maybe performances, but also portraits of composers, and so on. Obviously, music iconography lies at the intersection of a number of domains in cultural studies and the humanities, but it has particularly close affinities with art history and musicology, of course. What we will be doing today could be called computational or digital music iconography, maybe even distant iconography, in an analogy with what is happening in literary studies nowadays. We don't know of much explicitly computational work in music iconography, so we think there's still much to contribute from the digital humanities and computer science. We should mention, however, that this field has a number of interesting digital resources, in particular the RIDIM database, which was our point of departure, even a source of inspiration for this initiative. This database offers an international repertory of music iconography. It holds a large number of photographs of objects from the visual arts that depict musical instruments, and these instruments are identified with a specific code in the database, an unambiguous identifier, which is very useful. And these codes actually usher in the topic of the next slide, because this classification system has actually been developed in another project, the MIMO project, which stands for Musical Instrument Museums Online. This was and is a large European collaboration that proposed an ontology for musical instruments. And they also have this wonderful aggregated database online with lots of pictures of actual instruments in GLAM institutions from all over the world. If you have a minute, feel free to browse this amazing collection online. It's really wonderful. The MIMO ontology is organized on 2 tiers. On the lowest tier, we have a unique code for every musical instrument that exists, like a viola or a transverse flute, including a lot of exotic instruments that I personally had never heard of. You wouldn't believe how many different instruments are in fact out there. And then there is also a second higher layer where these instruments are grouped in larger, more general categories, like stringed instruments or electronic instruments. And that is what we call the hypernyms. These MIMO codes are very important because they underlie much of the work that I'll be presenting today. So it's crucial to acknowledge how dependent we are on this classification system. Today, we will talk about 2 tasks in this area, which we have taken from computer vision, the domain in computer science that is concerned with the analysis of visual data. The first is that of object detection. We would like a computer to be able to detect an instrument in an image and localize it by drawing a rectangle around it. And that is what people in this field call a bounding box. You can see an example to the right. And then secondly, once the instrument has been detected, we would like our software to be able to automatically recognize it and categorize it or classify it using the system of unique MIMO labels. So there's 2 distinct but related tasks here. First, detection, and then classification. And of course, they could be combined in a single system. Note, by the way, that the classification can happen at each tier. We could recognize something as a violin on the first tier, but also at the less granular tier, just as a stringed instrument, and keep the classification fairly broad. These tasks are actually pretty basic and low level, but obviously they are a prerequisite for any kind of macroscopic work in this area. If you would like to be able to chart the rise of the guitar in art history through the centuries, like you would do with words on Google Ngrams nowadays, you first need to be able to actually spot musical instruments in raw images and recognize them. If you do machine learning nowadays, you typically still need a lot of example data or training data. Data that has been manually labeled so that your system can learn from examples and see how humans solve a particular task. In this case, we didn't have a proper data set yet, so we had to build one ourselves from scratch, from the ground up. That was a pretty intensive phase in the project, and for me personally, it was also the first time that I had to take part in such an effort, and we actually learned a lot in this process. I'll say more about that later. What we have created is a so-called benchmark dataset for musical instruments as they are depicted in the visual arts, without any restrictions regarding chronology or different media types. We named it Minerva after the Roman goddess of the arts, and also because that acronym played out well. Musical instruments represented in the visual arts. The dataset is freely available for researchers on Zenodo, and it has annotations for more than 16,000 musical instruments depicted in just under 12,000 images. In total, however, we only observed 172 unique instruments in our data. Also here, of course, 2 granularities are available for each annotation: the instrument label and the broader category label or the hypernym. To the right, you can see the distribution of the data, and as you can see, one of the problems that we ran into very quickly is the gigantic skewness of the data. The large majority of the annotations in there only belong to 3 instruments: the lute, the harp, and the violin. These are everywhere, it's insane. And you can see that from there onwards, the numbers drop quickly, and you have this insanely long tail of much less frequent instruments. How do we collect this data? Well, first of all, in close collaboration, of course, with the domain experts or the art historians and musicologists in the institutions that we work with. we gradually expanded the data in a concentric fashion. We started out with what we could get from the RIDIM database, which wasn't extremely large, or at least not from a computer science point of view, but very high quality, since the relevant instrument codes were already added by the music iconography scholars from all over the world. The only thing our annotators had to do basically was to draw the bounding box around the instruments in the image. We did that in a software called Cytomine, which was originally developed for biomedical applications, but this served our goals really well. From there, we expanded the dataset with local images from the museums in Brussels, on which we often had already less specific metadata available. And then in the end, when we noticed that we still didn't have enough data, we pulled out the big guns and we started scraping Flickr, which yielded a lot of images, but at the same time also a lot of noise that had to be weeded out manually in a later stage. So let us turn now to the first task that we experimented with, which was plane classification. So we took the annotations in Minerva and cut out all the bounding boxes that we drew in the images as separate cutouts or patches. As you can see in the examples above, this is pretty messy data. Often instruments aren't depicted in their entirety or in a heavily stylized, distorted, artistic manner. Sometimes instruments could also overlap in a single patch, so lots of issues here. This data is very far from the kind of clean, photorealistic data that is typically used in computer vision nowadays, which is very cool and interesting, but also really challenging. The main challenge, however, was the skewness of the data. If you train a machine learning algorithm, these learning techniques typically like data sets that are balanced, in which the different classes appear with roughly the same frequency. And this is clearly not the case in Minerva. From the distributions below, you can clearly see that we have much more stringed instruments, for instance, than electronic instruments, to give the most extreme example. For this classification task, we experimented with three established machine learning methods that were all variants of what is nowadays known as a convolutional neural network, or a CNN. Unfortunately, I don't have the time to explain the specifics about that architecture, but in a nutshell, what is crucial in this approach is that you analyze an image using a kind of pyramid. You start by looking for patterns in very small regions of the image, and then you start merging these small patterns into larger features as you move up this pyramid. And the final decision as to the classification is then taken at the top of the pyramid, where all these layers eventually feed into. So how well does that work? Here are the results for the three CNNs that we experimented with: a ResNet, an Inception v3, and an older architecture that is called VGG19. If you look to the right, you can see that at the hypernym level, we get pretty solid scores with an accuracy of around 75%. This is, of course, a relatively easy task, because there's only 5 categories, and some of these, like the electronic instruments, are severely underrepresented. That also explains why the F1 score is so much lower, around 57 points, and that is because this metric tries to account for the imbalance in the class labels. In the columns to the left, you can see that we experimented with different approaches to cope with this class imbalance, the huge difference in frequency between the instruments. If we include only the 5 instruments that are most common in the dataset, the scores are still acceptable, but the results quickly degrade if you start allowing more instruments. If we include all instruments, the results even become dramatic, with an F1 score of little more than 6 points. So this tells us that the task is theoretically feasible, but that we probably need much more data to learn it properly, especially for the many underrepresented instruments in the data. These numbers are important, of course, but what is maybe more interesting for scholars in music iconography is to try and visualize what the model has learned, what it pays attention to when trying to recognize these instruments. On this slide, you can find a couple of examples from something that is known as a saliency map. Using the concept of a heat map, it tries to show which regions of the image the algorithm has been focusing on when making its decision. The example on top, for instance, shows how the algorithm for a wind instrument, something that you blow in, is looking for the presence of the tone holes in the aerophone, which are often placed in this typical symmetric way. The lower example, on the other hand, shows that the presence of fingers can also be relevant, especially if these are stretched and a bit in an unnatural position. And these visualizations are a great way to peek into the black box of your machine learning algorithm. And there are even nicer examples in the second part of the presentation. So now it's time to move on to the even more challenging task that I'll be talking about today, which is object detection. Here, in fact, we perform two tasks at once. We detect the instrument and we try to recognize it. For this, we made use of a very straightforward, but very popular and effective object detection algorithm called YOLO, which stands for You Only Look Once. This algorithm is used in many places on the internet nowadays because it's reasonably fast to train and there exist fast implementations. And they can even be applied to video, as you could see in the slide. So here are the results for YOLO. As you can see, we evaluated our system using a number of less well-known metrics, such as precision and recall, which you might still know from information retrieval, but also this IOU thing, which stands for intersection over union. This metric will basically take the bounding box drawn by YOLO and see how well it overlaps with the bounding box in the ground truth. The very first slide in this slide is interesting because there we didn't do any classification at all. We were basically just doing instrument detection. So there the task is just draw a box around any instrument that you see, regardless of what it is exactly. Here you can see that we, for instance, reach a reasonable precision of 63 points. These scores are, of course, lower than what you see for similar data sets in the photorealistic domain, like the data sets on which they train self-driving cars and all that, but they are not all that much lower either, which is promising. For the hypernym categories below that, you can see that we also still get good scores for stringed instruments and wind instruments, simply because we have more data there. Finally, for some of the individual instruments, we are also able to report good scores. YOLO is, for instance, really great at detecting harps. So this makes sense, not only because we have a lot of harps in Minerva, but also because this is a very large idiosyncratic instrument that is basically hard to miss in an image. For many other instruments, however, like the sham, the scores are much lower, so that in the end, the current applicability of this method really depends on what type of instrument you are interested in. Again, these quantitative metrics are very important, but it is also worthwhile to look at the results from a more qualitative or interpretive angle. And for this, we applied the trained object detector to two data sets that were not included in Minerva, so that we could find out how well the system would perform in the wild, given data from collections that it has never seen. And this is what we call an out-of-sample application in machine learning. This was very cool and interesting, and in fact I think we are now arriving at the most interesting, even fascinating part of the talk. First of all, we noticed that the system was very greedy. It was only trained on images that actually contained instruments, so it would try very hard to find instruments, even in images from artworks that didn't depict any musical stuff at all. This kind of errors is known as false positives, or when the algorithm dreams that it sees an instrument, whereas really there isn't one to be found. Now, interestingly, there were clear clusters or patterns in the places in which it erroneously detected instruments. And often there were quite obvious contextual clues that tricked the algorithm into seeing instruments. And I would like to talk you through some of these groups of errors. First, geometry was very important. Whenever there was a regular geometric pattern in the image, like the folding lines in clothing or the spikes of a wheel, the algorithm would think it saw an instrument. So probably these regular patterns reminded the algorithm of the appearance of strings, or maybe the conical shapes of drums. A second clear example were books, which in this new sample were very consistently tagged as instruments. In a way that makes sense, we quickly realized, because the iconography surrounding books and instruments is very similar. There we have heavily stylized, fine-grained close-ups with the clear presence of hands and fingers in a very outspoken position. These hands present something that is being foregrounded by the artist, so there are definitely parallels there. Then here are some additional examples, and these are actually my favorite. If you look at the top row, you can see that human bodies, especially naked bodies, and often of women, were tagged by the algorithm as stringed instruments. And if you think about it, that also makes sense, because the curvature of these bodies is highly similar to the conical shape of the resonance box of a stringed instrument, like a violin or a cello. If you look closer at these shapes, you will see that this is almost a forgivable mistake. Finally, and I really love this one, is baby Jesus. So throughout the additional sample of images, we saw that children, and in iconography this is mostly baby Jesus, were tagged as instruments. So apparently the way these children are depicted shares iconographic characteristics with the way instruments are depicted. These children, like instruments, are intimately held by a caretaker, and the body posture of these adults is very delicate, protective often. They are presenting something that is culturally salient, something that they care about, that is dear to them, something that they wish to protect. And we thought that it was very surprising that our method, as such, indirectly drew this insightful parallel between music iconography and baby iconography, if you will. So it's time to wrap up. All our code, data, and fully trained models are up online on Zenodo and GitHub, so feel free to play with them. We hope to have shown that the application of this technology is still pretty difficult, but generally also feasible and perhaps even meaningful already. In the future, we hope to improve our system by also looking at more photorealistic depictions of musical instruments, so actual photographs of instruments. And the MIMO database seems like a great asset to experiment with that kind of transfer learning, where you try to transfer knowledge from the photorealistic domain to the artistic domain. We are also expanding our data further right now. We are annotating new categories, for instance, like types of fruit and different kinds of mammals in art. But all in all, it seems crucial to arrive at a better balance and less skewed data sets by moving away from the small canon of Western instruments and open up to a more diverse group of musical cultures. So that's it, everyone. Thanks for listening. I hope you enjoyed the talk, and I will be very happy, of course, to take questions during the live session. Speak to you soon. Bye-bye.